Continuity. Here we go back and look at when we discuss limits in Calculus 1, where you had a function of y that depended on one variable x. But now we have a function z that depends on x and y. And so now, without the imagery being based on linear graphs, here we base the limitation on some region in the xy plane. We call it a disk. And we look at its delta neighborhood. So not just a line anymore, but a ball, a disk that rotates around the center point. This center point being x naught, y naught. And we want to be able to establish this open disk. And we limit this disk or this so-called circle or ball to be less than delta. Delta becomes the restriction. So if we can find points about x naught, y naught around that particular value as we keep changing delta. Matter of fact, we want to shrink delta as small as possible. And if we can continue to find points within that particular area, we say that we have continuity. And does that imply the shrinking about x, y? Does that also imply the shrinkage around some value for z? That value for z would be the limit. So does the shrinkage within x, y, does it imply also the shrinkage or the measurement about some neighborhood in z? We call that the so-called epsilon neighborhood. Let me pull up a graph that depicts that. So here I have this center, x naught, y naught, and if I can draw a disk, the disk has a radius, the radius is delta. So can I, when I create this delta neighborhood, can I find points about x naught, y naught? We call this boundary with respect to delta, we call it some neighborhood, and we're looking at this center point being x naught, y naught, and then we draw some epsilon disk around it, and can we find points within? So here the boundary and interior points of a region R. We've spent a lot of time in this course talking about this region R. Why is that important? Because within this region, you may have gas, fluid, and other type forces that depends on the boundary. The boundary will be important. So we will investigate two things in this course: what happens along the boundary, but then what happens also in the interior. And is there a connection? We'll find out that there is a connection. So I digress. What about the limit? If you look at the definition here of this, of the limit of a function that depends on two variables, it says, let f be a function of two variables defined, except possibly at x naught, y naught. It is okay that the function may not be defined at x naught, y naught, at that center point. But the function is defined in its neighborhood. That is, that I can find points, interior points within, then it's okay. I can still investigate the limit as x and y approaches this center. So we say that that here this function exists at some center. It may not exist at the center, but about it on some open disk. This open disk has a radius of delta. What is this square root of x minus x naught squared plus y minus y naught squared? This is just the distance formula. Right? This distance formula is computing here for us the distance from x naught y naught to the so-called boundary value on the disk. This distance is what this square root is computing. Yes, sir. And why is that important? Here's why it's important. I'm going to keep on shrinking delta. I want to get delta as small as possible. And if delta is small, that means that my neighborhood about x naught and y naught is small. Can I still find values within? If that be the case, does that also imply the distance from the function values to some number L that ultimately we'll call the limit? So does the shrinkage of delta imply the shrinkage of epsilon? I mean, that's the same terminology in Calculus 1, we investigated the limit there. But back then, it was only the absolute value of x minus a, or x naught, is less than delta, implies the absolute value of f of x minus L less than epsilon. Right? So now we have a function f that depends on two variables. And so because of that, we have this disk, or some ball, if you will. We have all these balls accumulated around this x naught, y naught. And in analysis, we call x naught, y naught if values exist if I keep getting these points about this point x naught, y naught, we call x naught, y naught an accumulation point. If I keep on shrinking delta, if I look at this neighborhood, if I look at that neighborhood, this neighborhood, this neighborhood, this neighborhood, keep on until I get just the smallest neighborhood. But does that also imply that as I shrink the values of the neighborhood about x naught, y naught, does that also imply the shrinkage here? That's the key. And so as I get close and close to x naught, y naught, how do I get close? I keep shrinking delta. So as I squeeze here about x naught, y naught, is there also a squeezing of the measurement, the length between here L plus epsilon and L? Does that shrink? Well, if so, do I end up with this number L up here in my space? Well, if I do, then we have a limit. Sometimes you can shrink about x naught, y naught, and the values about the z values, they get larger and large. And so thus you conclude the limit does not exist. I'm sorry. Yes. Okay. If the limit does not exist, you can have good things happening about the center point x naught, y naught, but it may get crazy up in the space. And that's when we say that the limit does not exist. Right? Well, with the idea of the limit, we can also talk about continuity. And again, the definition that I've given for continuity is the same here. That is that the limit of the function at the values x naught, y naught, that this limit exists. The function value at x naught, y naught is defined. And then thirdly, the limit of the function as x and y go to x naught, y naught is the function value. Now, what are they saying there? They're saying that if I plug the values of x naught, y naught into the function, I don't get 1 over 0. That's what they're saying. They're saying when I plug the values of x naught, y naught into the function, it exists. And then also, the limit of the function as x and y approach that same point x naught and y naught is the function value. They're the same. That's continuity. Now, let's look at some problems. Use the definition of the limit to verify the limit. So the definition says by definition, the limit as x and y approaches 4 comma negative 1, the limit of x, here this is equal to 4 if and only if for all epsilon positive there exists delta positive such that 0 is less than the square root of x minus 4 to be squared plus y minus a negative 1 to be squared is less than delta. Does that imply that the absolute value of f of x, y, which is just x, minus 4 is less than some epsilon? The question is this true? So we prove it. What are we proving? We are proving that the assumption implies the conclusion. And in doing so, we must find a suitable delta to satisfy epsilon. Can we find a suitable delta? To satisfy epsilon? Well, we're given the absolute value of x minus 4 to be squared plus y plus 1 to be squared is less than delta. This implies that the square root of x minus 4 to be squared is less than delta, and the square root of y plus 1 to be squared is less than delta by the triangle inequality. The triangle inequality says, you recall from calculus 2, that if I have a triangle, the sum of two sides of any triangle is always greater than the third side. Right? That's the triangle inequality. So here, this square root is measuring a distance. Right? So this distance here, if it's less than epsilon, then a piece of that distance is what is less than delta, excuse me. If this total distance is less than delta, then a piece of it is also less than delta. Right? And then the other piece is also less than delta. Over here, y plus 1 to be squared. I just took this part right here. Yes, sir. No, you're fine. It's kind of fuzzy. Now, if that's the case, then this square root of x minus 4 to be squared is equal to the absolute value of x minus 4. And the square root of y plus 1 to be squared is equal to the absolute value of y plus 1. So we get, I'm looking at this piece right here, we get the square root, not really. We get the square root of x minus 4 to be squared. This guy is equal to the absolute value of x minus 4. But we said that the square root of the absolute value, well, the square root of x minus 4 to be squared is less than delta. Choose delta to equal to epsilon, and we get it. That is, we have the absolute value of x minus 4 is less than epsilon. So the assumption implies the conclusion. We found the suitable delta. Here, delta is the same as epsilon for this particular problem. Very easy, 1. But I'll leave it at that. I won't go any deeper with that. But if you recall from Calculus 1, it's the same argument there from Calculus 1 to this. But now we just have two variables, x and y, implying something that happens out in space. Okay? Use the indicated limits to find the limit. Here they give you the limit of f of x equal to 4 as x and y go to a and b, and the limit of g of x, y equals to negative 5 as x and y go to a, b. So now can we find here the product? Well, the limit of the product is the same thing as the product of the limits. So this is the same thing as the limit as x comma y go to AB of f of x, y times the limit as x comma y go to AB of g of x, y. Well, the limit of f of x, y is 4, and then the limit of g of x, y is negative 5. So we just get negative 20. So there you're just computing the limit. Let me give you this one to do. Use the indicated limits to find the limit, the same given information. what's the limit for this quotient? All right, you should just get negative 1/4, right? Okay, very good. You see that? That's just 4 minus 5 divided by 4. Find the limit and discuss the continuity. Here, this is a polynomial function, so it's continuous everywhere. So since it's continuous, I can evaluate the function at the limit values of negative 1 and 1. So here, just have negative 1 plus 4 plus 5. Just get 8. The function is continuous everywhere. Now sometimes that's not the case where you can just plug it in. We hope that we can just plug it in and just get the limit and be done. But sometimes you plug it in, you get an indeterminate form. So you have to do some work, like you may get 0 divided by 0, or you may get something that's undefined, like 1 divided by 0, but you can do some work to it to somewhat clean it up. So we find this limit. If we plug in the values, x equal negative 1 and y equal to 2, so I have negative 1 plus 2 over negative 1 minus 2. So we just get 1 over negative 3, or negative 1/3. What about the continuity here? Can you explain the continuity for this function? Right, so it's continuous everywhere except when x equal to y, right? Except when x is equal to y. Okay. Continuous everywhere except when x equal to y. Any questions so far? All right. You find that limit and then tell me where is this function continuous? Okay, what's the limit there? 1 over the square root of 2. That's right. And what about the continuity? Yeah. X plus y is what now? Even I got it wrong. X plus y is greater than 0. Can't be equal to, because if it's equal to, you get something divided by 0, right? Yeah. even I erred. What are you doing? Okay, the mouse, having some issues with the mouse. Oh boy. Now I think it just froze. That's not good. I'll do more than read it. Okay. Well, let's see if we can do this and see, get to the point where I left off. And okay. Find this limit. If the limit does not exist, explain. Now, if you plug in here, x equals 0, y equals 0, you get 0 over 0. That's an indeterminate form. You have 3 possibilities for an indeterminate form. What are they? You have three possibilities to solve. In terms of an indeterminate form, there's numerous of those forms, right? 1 to the infinite power is indeterminate. Infinity raised to infinity. I'm not talking about that. What do you do when you have that? I said you have three possibilities. What are they? You can factor, you can rationalize, or you can use L'Hopital's rule. Right? Calculus 1, we talked about if it's indeterminate, you can factor, you can rationalize. You factor if it's factorial, if it's factorable, excuse me. You rationalize if there's radicals, right? And then thirdly, you can use L'Hopital's rule in any of that. Now, you can use L'Hopital's on that. So if we have an indeterminate form, we have three possible methods for solving. 1, factoring. 2, rationalize. Then 3, L'Hopital's rule. Here, since I have radicals, I'm going to rationalize. So this is the limit as x comma y goes to 0 comma 0. This is x minus y over the square root of x minus the square root of y times the square root of x plus the square root of y divided by the square root of x plus the square root of y. This is the limit as x comma y goes to 0 comma 0. The numerator I leave as it is, x minus y times the square root of x plus the square root of y. This is all over. Multiply the bottom and fold that out. You end up with x minus y. Now that cancels out with x minus y there. So I have left the limit as x comma y goes to 0 comma 0, and I have here the square root of x plus the square root of y. Now I compute the limit here as x and y goes to 0 comma 0. I end up with 0, and 0 is 0. It's not 1 over 0, which is undefined. It's not 0 over 0, which is indeterminate. 0 is a number. Do you remember rationalizing when you had that back in Calculus 1? All right. You find this limit. Since there's a radical, you can rationalize, or you can just take L'Hopital's if you want. Just be very careful of that that derivative downstairs. How would you take that derivative of x and y? We haven't talked about that. So you have to rationalize. Christopher, what'd you get? No? John? 0? Josh? I got 2. Donnie? Let's see, you get 2. When you check that, you do get 0 over 0 is indeterminate. So we take the limit as xy goes to 2 comma 1. I'm going to rationalize, so this is x minus y over 1 over the square root of x minus y minus 1 times the square root of x minus y plus 1 over the square root of x minus y plus 1. This is the limit as x comma y goes to 2 comma 1. I'll leave that numerator as it is. Multiply that denominator out, you get x minus y minus 1. And the first times the first, outer times the outer, inner times the inner. The outer and the outer and the inner and the inner, they cancel out. So you have basically is the first time the first minus the last time the last. Now we plug in x equal to 2 and y equal to 1. I get the square root of 2 minus 1, and then on the outside plus 1. That's the square root of 1 is 1 plus 1. I just end up with 2. All right. Let me work 2 more and then we'll get out of here. Use polar coordinates to find the limit. Hint, let x equal to r cosine theta, y equal to r sine theta. And so as x and y go to 0 comma 0, that implies that r goes to 0. So we convert this to its polar form, the limit as r goes to 0. The numerator is r to the third cosine theta sine square theta all over r squared. This is the limit as r goes to 0 of r times cosine theta sine square theta. Now the reason that they convert is when you have x squared plus y squared, it's easy to use polar coordinates. But again, you get 0 over 0. That's an indeterminate form as well. So the limit here, notice that r is the one that's tending to 0. There's nothing discussed about theta. So theta is treated as some constant or coefficient. So now as r goes to 0, here I have the limit of 0 times cosine times that sine square, and 0 times anything is 0. Now let me do one more where this problem sets you up for what happens in the next section. This is the definition for a partial derivative. You remember in the previous section we had this guy, but there was no limit in front of it. Right? So no limit in front of it meant that it was just the slope of a secant. Put the limit in front of it and we get the slope of the tangent or the derivative. So if I do part A, and that's all I have time to do, just have 2 minutes. So part A, I want to find the limit here as delta x goes to 0 of f of x plus delta x. I look at the change with respect to x. I treat y as a constant minus f of x y all over delta x. So this is the limit as delta x goes to 0. Here, wherever I have x, I'm going to write x plus delta x. That's to be squared minus 4y. That takes into consideration the f of x plus delta x comma y. Then now is minus f of xy. That's minus brackets x squared minus 4y all over delta x. Just simplify that now. This is the limit as delta x goes to 0. This is x squared plus 2x delta x plus delta x to be squared minus 4y minus x squared plus 4y all over delta x. A couple of things cancel. X squared minus x squared goes out, minus 4y plus 4y goes out. Since my time is limited, I'm going to factor out a delta x and then divide that out. So this is the limit as delta x goes to 0 of 2x plus delta x. And this is equal to 2x as delta x goes to 0. Now, if you come back and look at this function here, and if you take the derivative of this with respect to x, and you treat everything else, treat y like a constant or coefficient, take the derivative of x squared, don't you get 2x? So that will become the partial derivative, and we'll talk more about that. In the notes, there's a problem for you to do. Make sure you do that, and then do the homework online, and come back tomorrow, Thursday, and tell me about it. Thank you. Yes.